So far, we've covered the first three parts. Before diving into the fourth part, let's do a quick summary. In the part about QAC, the main focus was on the concept behind the Actor-Critic framework. In the part about A2C, the goal was to highlight the use of a baseline to reduce estimation variance. In the part about off-policy Actor-Critic, the primary purpose was to introduce the important sampling technique. You may have noticed that when discussing policy gradient or gradient ascent, I went over them quickly because they are very similar to what we've covered earlier. I didn't go into much detail on these aspects. One common feature of the first three parts is that the policies are always stochastic. That is, pi as theta is strictly greater than 0 and will never be exactly 0. Now let's introduce another important method, deterministic Actor-Critic. This is what I mentioned earlier and I won't repeat. Up to now, the policies used in the policy gradient methods are all stochastic. Can we use deterministic policies in the policy gradient methods? The answer is yes. But why should we care about deterministic policies? To illustrate this, let me show you a figure. Previously, our policy was pi, which took state S as input, and outputted a distribution over actions, such as pi a1s theta, pi a2s theta, and so on. If there are 5 possible actions, the policy outputs 5 values, each strictly greater than 0 and their sum equals 1. This is the type of stochastic policy we've been working with. The limitation is that it requires a finite number of actions. The policy can't output an infinite number of actions. What if we have infinite possible actions for a given state? In that case, we can use a deterministic policy. To be more specific, all our policies were represented as pi as theta, which gives the probability of taking action A in state S. This is a value between 0 and 1. It may represent a stochastic policy or a deterministic policy. Now, to specifically represent deterministic policies, we directly denote the policy as A equals a mu S theta. Here, mu is a function that takes a state S as input and theta as parameters, and outputs an action A. It must be noted that mu is not the probability of taking action A in state S. Instead, it directly outputs the action itself. For instance, it may output an action to move up or down, or an action in the action space. So, mu is a mapping from the state space to the action space. When the state is determined, the action is also determined by this function. This is the key distinction between stochastic and deterministic policies. In practice, the deterministic policy can be represented by a neural network with parameter theta, where the input is state S and the output is action A. Sometimes we write mu S theta in short as mu S to hide the parameters. Next, we need to answer 2 questions. The first is how we compute the gradient, and the second is how to apply this gradient to gradient-based algorithms for optimization. This is very similar to the previous methods we've covered. In fact, gradient-based optimization methods are widely used in reinforcement learning. Once you understand this general approach, many other algorithms will become clearer. The policy gradient expression we derived previously was for stochastic policies. Now, if we require the policy to be deterministic, we need to derive a new expression of the gradient in this case. The basic process of derivation is similar to what we did earlier. First, let's define an objective function j theta, where theta represents the parameters of the deterministic policy mu that we want to optimize. The function is defined as the sum over all states. J theta equals sigma d0 sv mu s, where v mu s is the state value under the policy mu, and d0 is a probability distribution that satisfies d0 of s is greater than or equal to 0 for all s, and sigma d0s equals 1. The distribution d0 can be chosen in 2 ways. First, suppose that we're only interested in a specific state, say S0, because, for example, every time the agent starts from this state. In this case, we can set d0 as 0 equals 1 and d0 of s not equal to s0 equals 0. The objective function here would simply be v mu s0, which means we aim to maximize the return we can get if the agent starts from s0. Second, we can select d0 as the stationary distribution of a behavior policy. For example, another behavior policy, let's say beta, has its stationary distribution as d0. you'll soon see that the deterministic policy gradient method is inherently off policy. I don't need to use importance sampling to convert it into off policy, it's naturally off policy. Why is that? You can actually see some clues in this gradient. This is the expression of the gradient of the objective function. How is it derived? You can find the details in my book, and I will not talk here. For most of you, it's enough to just be familiar with this expression. Those who are interested in detailed derivation can check my book. In the discounted case, when I compute the gradient, it is equal to this. Let's have a look at it. This is an expectation. The state S follows a distribution rho mu, whose details can be found in the book. This term consists of two parts. The first part is the gradient of mu with respect to theta. The second part is the gradient of q mu with respect to A. Note that there are brackets in this term. Outside of the brackets, there is a line where A should take the value of mu s. What does this mean? It means that I first compute the gradient of q mu with respect to A, and then replace all instances of A with mu s. Some might ask, why not directly replace A with mu s? The reason is that if you do that, the expression will no longer involve A, and then it's unclear how to calculate the gradient with respect to A. Therefore, we write it this way. This gradient is quite different from the gradient in the stochastic case. One key difference is that it does not involve A. There is no action A in this expression because A will eventually be replaced with mu s. Therefore, without A, there is no gradient with respect to A. As a result, it leads to an off-policy algorithm. Why is it off-policy? Because later on we need to use a stochastic gradient to replace the true gradient. When we calculate the stochastic gradient, we need to perform sampling. If state S is given, then I can sample an action A and then obtain the reward RT plus 1, and so on. However, I don't care which policy generated the action A here. This is because the expectation does not require to sample A. It can be sampled by any policy. Therefore, I can use a behavior policy, which can be any policy. Once we have this gradient, we can apply a gradient-based algorithm to optimize the objective function. The gradient ascent algorithm is theta t plus 1 equals theta t plus alpha theta, which is the step size, and the following is the gradient. This is the expression we derived earlier. Next, since we have an expectation here that we don't know, we can replace it with a stochastic gradient. The corresponding algorithm is as follows. Let's go through it. There is a behavior policy beta, and at each step, beta generates some data. We use this generated data to compute a TD error. This TD error is passed to the critic, which then updates the value estimate. This is actually an algorithm that we've learned before. TD algorithm combined with value function approximation. Once this Q is updated, we apply it to the theta update algorithm that was given earlier. Now, let me make some additional remarks. First, I need to mention that this is an off-policy implementation. In this case, the behavior policy is beta, and the target policy is mu. In practice, you may also replace beta with mu. In such a case, once I obtain mu, because mu is deterministic and cannot explore, I can add some noise to it. For example, if mu deterministically directs the agent to move in this direction, I can add some noise so that it moves slightly to the left or right, allowing for some exploration. Then, the agent moves to the next state and performs sampling. This is essentially an on-policy implementation. Since this is an off-policy algorithm, it can be implemented either off-policy or on-policy. The idea of mu plus noise is actually very similar to the epsilon greedy method we discussed earlier, but we cannot use epsilon greedy here because the actions are continuous. Another remark involves the calculation of Q within the gradient. How do we select Q? There are two ways. The first way, which was widely used before and also used in the original paper that proposed DPG, is to use linear functions. That is, Q equals phi transpose multiplied by W. Here, W is its parameter, and phi is a feature vector. The problem with this way is that first I have to choose a feature vector, and second, because it is linear, its ability to approximate the true action value is limited. Thus, the second way, which is widely used nowadays, is to use neural networks. In fact, this paper extended DPG to deep DPG, which is called DDPG.